Good morning, everybody, and welcome. It's great to see the participation in this event. We've got people from across the state in Nebraska and across the United States, and a few of our global partners joining in. My name is Peter McConaughey. I'm the Executive Director of the Daugherty Water for Food Global Institute here at the University of Nebraska in Lincoln. We're excited today to recognize the research achievements of our students funded by DWFI's Student Support Program, as well as hear from some current leaders in science and communication. All participants will be muted, but please do post comments in the chat box or ask questions in the Q&A box located at the bottom of your screen. Our vision at DWFI is for a food and water secure world through science and policy research, outreach, and using research results to inform policymakers, sharing knowledge through education and communication. Each year, we provide financial support to students working on various elements of the water and food security on projects that contribute to our mission of having a lasting impact on achieving more food security with less pressure on scarce water resources. The emphasis there on impact. Our impact is achieved in part through the efforts of these students and their professors. This is actually one of our largest, it is our largest program of support out with the Institute itself. Up to date, we've invested getting close to $3 million since 2014 through more than 80 awards supporting postdoctorates, graduates, and undergraduate students on all 4 University of Nebraska campuses. Most of these dollars have been matched by faculty themselves, furthering the impact of the research we do here at the university. Beyond the data, research, and journal articles, we know the incredible impact that science can have on our world. We have seen this come to light even more so over the past year. And today we're excited to hear some reflections from astronaut Clayton Anderson, who's a native Nebraskan, and Nebraska State Climatologist and DWFI Faculty Fellow, Martha Shulski, both leaders in their respective fields. We will then hear from DWFI supported students near the completion of their research projects and have some time for Q&A that you all can participate in. While we can only highlight a handful of students today, you can view research impact summaries of each of the 30+ students that are currently being supported. This is on our website through the link provided in the chat box below. We hope you come away today excited about how science can change the world and inspired by cutting-edge research being done by our students, the future leaders in water and food security. With that, I'd now like to hand it over to our Director of Research, Christopher Neal, who leads the DWFI Student Support Program. Christopher.
Yeah, thank you, Peter. Good morning, everyone. I just wanted to outline a little bit of this program that started in 2014. And that was my first year as a director of research. And the need is, fairly evident for us that we're an institute that one of our missions is to further the research and scientific and policy research. And so investing in young scientists is part of that, right? We want to find solutions to help manage water and food resources in the future. And this program was a way to leverage the funds from DWFI, from the generous gift of the Robert B. Daugherty Foundation towards our mission. And as Peter mentioned, the students, the program is matched by faculty fellows that apply for the funding with proposals for funding the MS and Master's and Ph.D. students. And so far, we've invested approximately since 2014 about $400,000 a year between our resources and the match resource by the faculty, funding over 80 projects and 93 graduate and undergraduate students, some postdocs at the beginning of the program. And then there has been a lot of outputs in forms of presentation and publications over time, and that still continues. And the impact of this is going to be felt throughout the future as journal papers get references and so forth. And looking at our impacts, our previous program manager, Lacey Bonner, had put together this infograph where she had looked at where the students had ended up professionally after they finished their degrees. And you can see down here the different professions and different things that they got involved in. And so this helps to raise the profile of the institute and of the university. This latest funding cycle, the one from this year, had two different tracks. There was a new water, climate, and health track, as we have this the new director, Jesse Bell, in this new program. And so faculty could apply to one track or the other. We received about 15 applications, went through a review process, and so the reviewers rank the proposals, and then we do a master ranking, and we fund up to what we can with our resources. And I thank you for the reviewers and also for the donors. And Peter put a list of all the different foundations and donors. And in particular, Claire Hubbard, who has been funding the Water, Climate, and Health track students through this program. So we have 13 funded projects, and the notifications will send out in March. And so next year, hopefully you'll be hearing more about these research projects, as we have some of the presentations today from previously funded projects. Now we will move on to the second speaker of the program this morning. We will hear from Nebraska State Climatologist and DWFI Faculty Fellow, Martha Shulski. She's an associate professor in applied climate science at UNL in the School of Natural Resources. She also serves as the director of the Nebraska State Climate Office, which delivers science-based weather and climate information. Her research interests include climate variability and climate impacts, understanding the causes and drivers of variability and how this variability influences historical trends in climate. Also how these changes impact our society and environment. She has a strong interest in understanding information needs and working closely with users of weather and climate information to deliver sustainable support tools so that the data and information can be used. So Martha, welcome. You have the floor.
All right, thank you very much. So I'm going to talk a little bit about kind of what I do as the state climatologist. I'll talk less about science and more about communication of science. And I will preface this by saying that I am trained in the fields of meteorology and agronomy and soils and climatology. So notice that you did not hear communication in that. All of the examples that I'm going to be talking about and what I'm going to be sharing today really comes from just 20 years of communicating with people on what can be kind of a controversial topic. And so that's one of the points that I'm going to be making today is some of the individuals that you might be talking to about your science might disagree with you. And so I'll talk about some strategies to help through that. So obviously I work at a university, I'm faculty, and I write grants and write papers and do all those science kinds of things. But what I also do, what's a big part of my job, is interacting with people. So on this image here, you see two circles. You see kind of the science world, which is what I mostly exist in. But I also work in what I consider a boundary organization. And so majority of the people that I interact with are end users of the information that I either personally help put together or help synthesize information on what can be a pretty complex topic of climate and climate change, especially. So I exist kind of at this intersection of where science meets people, and people are making decisions based on this science. And so what I do is provide them with this science-based information. So often I tell audiences that I'm a translator. You can find any information you want to on the internet. And so my job is to, again, provide the science background and translate it into something that is useful for individuals, for organizations, for lawmakers, policymakers, a whole range of people that I regularly engage with. So what you see on this slide here is kind of a reflection of that. So going from raw data that we take from this network of weather observations that we have all across Nebraska, which our office manages, or information all across the globe, and taking that and turning it into something that is usable by people. So the image that you see on the right is to help answer that question that I often get, is what does climate change mean for me in Nebraska? It's a very complicated question, and you're seeing kind of the elevator speech version of that answer, but that's just to help illustrate what I do, is translating science into something that somebody can actually use. So I'm going to be focusing mostly on communication and just some things to think about. You know, you're a scientist, you're doing your research, but how do you communicate that research to individuals, to your family, to your coworkers, to people that are funding the research? You may find yourself talking to a presidential science advisor, which I did a couple of presidential administrations ago. This is John Holdren, who was Obama's science advisor, and he was visiting campus and he's touring one of our weather stations. When you're communicating your science, the number one thing to think about, in my opinion, is knowing your audience. Who are you speaking to? What is their background? How do they feel about this topic? You know, particularly if it's something that may be controversial, how do they feel about it? Being relatable to who you're talking to and connecting to them, you know, thinking beyond the science, but just how do you relate to that person and connecting with them in a meaningful and lasting way. You can still provide the same amount of scientific content, but you can take away the acronyms, the technical terms, all of that might confuse people or just cause them to disbelieve you. Extract all of that and just approach it in a very relatable way, like you're somebody's friend and not their chemistry professor, for example. So that's one important consideration, I think, is connecting with who you're talking to and being relatable to them, whatever that audience is. So relevant, when you're talking about the importance of your science or the experiment that you've done or the work that you've done, don't think about it in terms of writing a research peer-reviewed article, okay? You do not start with your data and observations and the process of how you got there, your methods. You know, turn that outline of what you would write for a peer-reviewed manuscript and flip it around. Think about the discussion at the very end and why it matters, why it's important. That is what you should start with. When you're communicating your science to this general audience, start with why it matters and not how you got there. Because if you go through all those steps, you're probably going to lose people in the process. So I'll just give you an example from my world. I talk a lot about climate change to a lot of different audiences. So one of the things that I do is, why does it matter? Historical trends in Nebraska, we've gotten a lot wetter in the state, particularly in the springtime. The image that you see here is from the Sandhills, and there's a road that's underwater. This is why it matters. This is why it's important. There are communities that are flooding from below and from above, from groundwater coming up and from too much precipitation. Just one example, one concrete example of why climate change matters in Nebraska. So start with the why, and not this complicated image that I've brought up here on the right, the upper right part of the screen, which goes over the details of setting up a weather station to know that we have these precipitation trends. Skip the methodology and save that in case somebody does have questions about that later. You can have that in your back pocket, but don't start with how you got there. Start with why it matters and making it relevant for that audience, whatever that audience is that you're talking with. Okay, so think about the overall approach that you want to use when you're communicating with audiences. What frame are you going to put around this picture of your research? So think of your research as a Picasso, for example, or pick your favorite artist. What frame are you going to put around that? How are you going to present that material to the audiences that you have? So framing is really important. It's critically important in my profession. Half the people I talk to or talk with will disagree with me. And so I use a different frame for those audiences as opposed to the ones who do agree with me and are concerned about climate change and want to find solutions. So think about that frame for your picture of science that you have. And also make the abstract concrete. A lot of the research that you're doing, it might seem very intangible. It might not have direct relevance for people, might not be able to see a connection maybe in their daily lives or what's important to them. So if you're working with something that is abstract, which a lot of science is once you get into the upper levels, obviously, but make that abstract something that is concrete, something that is tangible, it is local, and it is relevant, and somebody can actually understand and grab onto that concept that you're studying. That really can be impactful, is making out the abstract concrete. So the images that you see here, you maybe can guess the one in the upper right, that's from the flood of 2019. I use weather events a lot in my frame of the picture of climate change. Okay, somebody might not want to start a conversation about climate change, talking directly about climate change. So I start in from another angle and I talk about the weather and extreme weather events. And that's a way that we feel climate change. The image that you see on the bottom right, that's proxy records, that is carbon dioxide over the last 400 or 800,000 years. Carbon dioxide is a greenhouse gas, and people know that carbon dioxide is linked to climate change. But again, I don't start with that. I keep that in my back pocket. If somebody has a question about that, then I will bring it up and talk about it. So approach is, think about how you are going to approach and frame your science topic. Okay, something that's really important, critically important in the work that I do in regard to climate change is finding common ground. You know, when I started off in college 20 years ago, I never would have thought that I would have had to convince people that science is real, right? I never, that was never a topic of conversation in all the classes that I was going through, but it's more and more of a concern. And think about what's going on with the pandemic and other aspects of science. So dealing with people who feel differently than you, or who disbelieve in the science that you are trying to communicate, that is probably going to become an issue for you at some point. So there are ways to get around that. If it's something that is controversial, it's really important to listen first and to not go in there and pounding the pulpit and stating that your science is real and you must listen to me and you must change your behavior. What's really important about communication is listening. So listen first to whatever audience that you're talking to, understand where they are and gauge where they are on a scientific issue. maybe get them to start talking about how they feel on this topic, and empathize, show some empathy with that. Even though you completely disagree with them, that's okay. You can still communicate in a meaningful way to them. So empathize and then talk. I do this a lot with people who disagree that humans are causing climate change or that the climate is changing. And I get the person to start talking first. And typically what happens is they will talk and explain climate change and climate variability. And so I start where they are first, and then lead them to where I would like for them to go and understanding the science. The image that you see on the screen is a recognition of what's called the 6 Americas, the Yale Project on Climate Communication. They have surveyed the US population and have identified these 6 groups, categories of people. Luckily, it's trending toward more and more of the US population agreeing with human-caused climate change and understanding that it's an issue. However, most people don't feel that it harms them personally. So that's part of my job, is to illustrate that. But just recognize that you may have to engage with people who are doubtful or even dismissive of the science that you are describing to them. So just be aware of that going forward in your career. So one tool that I use, and it works for controversial issues in particular, but really I think it's a great tool to use for any sort of applied science, right? So not kind of the pure theoretical work, it's more the application of the science into some realm, into somebody who's making a decision. Just recognize that sometimes science is not enough, and you do have to go beyond that. There may be a period of time where you need to build trust with whatever agency you're working with or group, and so forth, and that takes time, and it is an iterative process. So the example that you see here is I engage with people and tell them that if we don't act on climate change, we will warm by 9 degrees approximately in 60 years. So the Nebraska climate, when my kids are my age, is going to be very different. And that's a hard concept for people to grasp and for people to accept. But developing a relationship and working with people, hosting workshops, and understanding what their needs are in regard to scientific information, understanding what their decision points are, and delivering the science that matches those decision points is really, really valuable. So relationship is something that maybe you don't think about too much in your scientific process, but when it comes to applying your science to a decision maker, to a funder, policy maker, think about relationship and that human side of things. We may not have a lot of social scientists in the group, and I'm not one, but really think of the importance of the human part of it. And I think that is where I will end there. There's my contact information. There's one of our weather stations from the Nebraska Mesonet. If I had my choice, that's where I would prefer to be, either talking to people or being out in the field and taking these observations. And I very much appreciate the time to speak with you today, and I'd be happy to answer any questions if there's time or if people have any.
Sure. Thank you, Martha, for that presentation and what's important when delivering the message to the stakeholders. I have a question on historical data that your center is collecting and looking at. In 2019, we had a rain over snow with frozen ground event that caused severe flooding and destruction of infrastructure and so forth. Looking back in time, was there another occasion, or did you happen to know when a similar event happened historically? in Nebraska?
Well, yeah, good question. It's not often that we get that extremely large scale event that impacts so much of the state. And springtime snowmelt is one of those. And summertime prolonged rainfall would be another one where we get this broad scale flooding event. 1993 was a good example of a flood event that impacted a big area. I think it was shifted a bit more to the east as opposed to affecting mostly Nebraska specifically. We did have a flood event in 2011 when we had a lot of snow in the upper Missouri Basin. And so that affected part of Nebraska. But the 2019 event was rare in terms of the spatial extent and the severity. The rivers, the crested, we had record, we had rivers that crested at levels that we have not seen before and covered such a broad area that we've just not seen before. And the setup that we had, the very cold February, the wet winter, the river ice, the setup was critical to that. In March of, just last month of this year, we had a storm that was quite similar to 2019. What we did not have this year was the setup. We had warm soils, we had dry soils, we had no snowpack. So we did not have that immediate snow melt along with that.
So I have another question regarding communicating with farmers, for example. Okay. In my opinion, farmers have been doing that for decades, right? And it's come down through the family and whatever. And they're the ultimate observers of climate, right? They're watching in the spring when it's time to work their fields or plant their crops and whether it's going to be dry and wet and so forth. So I would say that a lot of these indicators of climate change, they're aware of it, right? So how have your conversations with them go? Because sometimes they're part of a group that politically likes to follow a different message. Could you elaborate on that?
Yes, so I quite often talk to various farm groups. They are aware of it. So a couple of comments typically arise. And one is that our climate is so variable, it's very noisy, so to speak. And so identifying a trend, a signal among all that noise can be very difficult. So that's one observation that they do have that is correct, but that's difficult to overcome that, we're going up this escalator, we're jumping up and down, but we're still going up this escalator. Another factor is the human component in it, the cause of it. So if there's not a recognition that humans are causing an acceleration of climate change, then that is difficult to find solutions and to mitigate greenhouse gas emissions, for example. So that's another factor. And a third that I've found is sometimes the agricultural community blame is put on them as the problem for climate change, rather than bringing them to the table to figure out proper solutions. And so I think from what I've gathered, they do not wish to be blamed, but rather brought in on the conversation and craft a solution rather than being dictated and told what to do. But I find that the tide is kind of shifting, and I find agricultural audiences being more receptive to this information and being more inquisitive and wanting to work through solutions.
Yep, I agree with you. The agriculture, while now may be perceived as part of the problem, it is definitely going to be part of the solution in the future on finding ways of capturing more carbon and decreasing emissions. Thank you very much, Martha. Let's have a virtual thank you.
Thank you all.
And so now we move on to the student presentations. So we're going to have, these are short presentations. So we'll have 3 in succession, and then we'll have a question and answer period for those 3. And then we'll head on to another 3, right? So sort of a quick draw here. So our first presenter is Jeffrey Westrop. Okay, he recently defended his thesis named "Influence of Nitrate Inputs on Uranium Mobilization from Fluvial Sediments." Jeffrey is advised by Carrie Weber, Associate Professor, and UNL Biological Sciences and Earth Atmospheric Sciences. Jeffrey, please go ahead and give us your presentation. Thank you.
All right, well, thank you for that introduction. And again, I'll just be giving you kind of an overview of some of my dissertation research on uranium mobilization. And let's see. So uranium is a naturally occurring radioactive element, as well as a regulated groundwater contaminant. And levels of uranium in groundwater above the US EPA maximum contaminant level of 30 micrograms per liter have been observed in many US aquifers, including in eastern and central Nebraska. And so given the kind of health risks that groundwater uranium poses, it's important to understand what factors might be leading to the occurrence of uranium in groundwater. And as part of some previous DWFI supported research, I conducted some experimental column studies that demonstrated that inputs of nitrate, which is a groundwater contaminant that could source from such places as agricultural chemicals or septic tank waste, can catalyze microbially driven reactions that mobilize the sediment-bound uranium into the groundwater. But in these experiments, I used a fairly high concentration of nitrate. So another kind of aspect that I was wondering about this research was, how does the concentration of nitrate play into this? Basically, how much nitrate is enough to mobilize uranium from the sediments into the groundwater? So in order to do this, I again used an experimental approach. I used what are called batch reactors, which is just a fancy scientific term for a sealed jar with some sediments that contain a basal groundwater medium. And so in order to look at the influence of nitrate, triplicate reactors were spiked with increasing amounts of nitrate until uranium was observed in the aqueous phase. And then I also had some controls which were spiked with an equal amount of deionized water. So initially, adding a low amount of nitrate, around 7 milligrams per liter nitrate nitrogen, did not mobilize uranium to a significant degree from the sediments. However, adding twice that amount did mobilize uranium from the sediments. But this is something that we kind of expect. This is kind of your garden variety uranium chemistry. Adding nitrate should mobilize uranium. However, what I was more interested in is this area right here. What's going on at levels below this kind of threshold or tipping point for uranium mobilization? Why is there a different response? And so in order to kind of look at what's happening to uranium that's already in the aqueous phase, I used the same batch reactor design, except for that I added aqueous uranium to see if there's any interactions between nitrate and uranium that's already in the aqueous phase. And adding a low-level nitrate not only didn't result in any increase in uranium, but interestingly, the ones that received nitrate actually saw a decrease in the amount of aqueous uranium compared to unamended controls, which is kind of the exact opposite of what we'd expect. Conventionally, we would assume that adding nitrate would mobilize uranium instead of decrease it. So we need to kind of figure out next why this might be occurring. And one hypothesis is related to dissolved carbon, because in the nitrate-amended reactors, we see an increase in the amount of dissolved organic carbon. And this is significant because DOC, or dissolved carbon, can drive microbial reactions that may kind of do the opposite, would actually precipitate groundwater uranium back into the sediments and thus lower the groundwater uranium levels. And indeed, we see evidence for this as an increase in the abundance of microbial or bacterial cells compared to the controls. And while these experiments have a lot of additional data, And we're actually going through and looking at the microbial community and genomics right now, so we can see, what microbes are there and what they're doing. If there's kind of, a take-home point to this research and my entire dissertation, it's that while these sediment systems are very complicated, the amount of nitrate matters. High nitrate inputs can mobilize uranium from the sediments into the groundwater, but it's important to realize that not all nitrate inputs will mobilize uranium. In fact, low-level inputs can catalyze these complex biogeochemical reactions that may actually reduce uranium levels. Now, am I suggesting that we should just add nitrate to all uranium-contaminated aquifers? No. Nitrate itself is a contaminant, so that's not a very good idea. But if we're looking at the fate and transport of uranium in groundwater, it's important to realize that not all nitrate inputs will mobilize uranium. And in fact, the opposite can occur. And so even though the year of 2020 was very tough due to the pandemic, I did manage to present give a couple of presentations at international meetings at Goldschmidt and at the American Geophysical Union. And I have a couple of publications in prep from my dissertation, which is kind of the main thing that I got done. I defended my dissertation, and in May, I will be Dr. Jeff. So that's my presentation. Thank you for listening.
Thank you, Jeffrey. So we will have questions after the next two presentations. So all of you out there, load them up in the question and answer channel so that we can ask Jeffrey in a few minutes. So our next speaker is Jasreman Singh. He's a Ph.D. candidate studying soil and water resources engineering in the Department of Biological Systems Engineering. His research project title is what he will present today is Unmanned Aerial Vehicle Data Mule over a sensor node station network in maize and soybean. Jasreman is advised by Dr. Chuyang. He's an associate professor at the Biological Systems Engineering Department. Well, welcome, Jaz. You have the floor.
Thank you. So thanks for the introduction, Christopher. And I'm going to talk about the unmanned aerial vehicle data mule over a sensor node station network in maize and soybean. So recently, the wireless communication technology has contributed to the advancement of precision agriculture, and it has been highlighted as a potential tool for improving the efficiency and profitability of field crop production. The feasibility of deployment of these wireless sensor networks have made this technology highly desirable for military, agriculture, sports, medicine, and industry. And these UAS systems have found applications in various wireless application technologies. So the objective of the study that I recently conducted was to assemble a soil, water, and a crop canopy measurement system based on real-time monitoring. And these traditional wireless sensor networks would be connected to a radio, and this radio could actually further communicate with the airborne data mule that would be deployed on the drone. So this whole setup consisted of an engineering design that the mini laptop and the secondary radio, they were mounted over on the UAS. So this is the close view, and this is the field view. This is me and Mitch. We conducted this experiment, and we tried to establish the wireless communication with the stationary sensor node stations that I showed in the last slide, and I'll be talking about them in the further slides. And we retrieved a soil moisture and canopy temperature measurements from these stationary sensor node stations. So we had our node stations located at 5 different locations in the field. So this field is located at the University of Nebraska's Eastern Northern Research and Extension Center at Mead, near Mead, Nebraska. So this was the research farm, and we had 4 replications of the node stations on the south side where maize was planted, and one node station was on the north side where soybean was planted during 2020 growing season. And an attempt to establish wireless communication with each station was made while the UAS flew over each station. So we conducted the experiment at 4 different heights. That's 100, 200, 400, and 800 feet. So I have them written in meters over here. So like the major findings from the preliminary results were that the success rate of communication and data transmission was higher at 30 meters above the ground, that's 100 feet. I mean, as we go to the higher altitudes, the chances of interference from the crop canopy or adjacent power lines also increase. And we witnessed interference issues like the transmission interference issues from maize. But yeah, there were no as such issues from soybean. And in the future, I would feel that more testing and validation is required. So yeah, this summer we would be focusing on some more testing and validation. And this proposed approach of wireless communication could be deployed for public, private, or industrial Internet of Things applications. Thank you, and I'll be looking forward for the questions if you have. Thanks for your time.
Thank you, Jas, for that. We will invite people to ask questions for Jas so that when we have our round of questions after the next presentation, we'll conduct that part of it. Right now, we're going to move on to our next speaker, Osler Ortez. He's a Ph.D. candidate in the Department of Agronomy and Horticulture, studying corn ear development issues. And he's advised by Dr. Roger Elmore and Dr. Justin McMahon, assistant professor at UNL entomology. And Dr. Elmore is emeriti professor in the same department at UNL. Welcome, Osler. You can go ahead.
Thank you, Dr. Neil, for the introduction, and welcome everyone. So today I'm going to give a quick summary or a research update of what we have been doing for the last couple of years, thanks to the program Water for Food that has been a partner since the beginning of our projects. So from the distance, usually we can see a nice homogeneous cornfield. That brings us to our topic today, that if you get closer, you can start to see things or anomalies that we don't want to see. They decrease productivity and yields. So that brings us to our research project. Before moving forward, let's set the stage, and a few of us have been already discussing about corn in the US and particularly in Nebraska. So this map portrays the importance of corn for the whole country. We are looking at the percentage of national production for the years comprehended between 2015 and 2019. And the main message that we want to draw from here is that Nebraska is indeed in the top 3 producing states at the whole country level. So corn is important, and we want to maximize productivity and yields. With that, the background of our research project on ear abnormalities, it goes back to 2016 when abnormalities were being reported from growers' fields, particularly in Nebraska at that point. However, later on, more reports of these same type of issues were received from states that extended from Texas, Colorado, Iowa, and Illinois. In our research work, we are focusing on 3 major groups of abnormalities. They are listed here on your right section. The first group are short husks. Those are ears that have some level of exposure. Insect disease pressure will be harmful for this type. Our second group are multi-years. That's when you have more than 1 year on the same plant node. At a first glance, you might feel that it's beneficial to have these multi-years on a plant. However, the reality is that when you have this type of year, the production, grain production, is substantially decreased. And our third group are barbell years. Those are relatively new. We didn't hear a lot about those in the past, and we have a few subclasses on that group. So this takes us to our major and overall objective, which is to study the factors that are responsible for these abnormalities, and also study the impact that they have on productivity and yields. How do we do that? So since 2018 and 2016, we have been working in different approaches. We have established a grower service in Nebraska. We have worked with field research via university and also industry partnerships in the state. And more recently, we established also greenhouse experiments that can complement what we are finding in our fields. The factors that we have under study include hybrids, we have planting dates and seeding rates, all across several environments in the state. Now, I mentioned about yield earlier. So in this figure here on the x-axis, we have the different ear types. The brown bar are normal ears, what we would like to see in our fields. And the orange bars are showing those abnormal ears that we have been documenting and investigating over the last couple of years. On the y-axis, we are looking at the grain weight. In other words, how much production are we getting off from those different ear types? And as clear as you can see here, abnormal ears certainly decrease yield, 64 grams compared to 185, sorry. If we do a quick math on that, that takes us to yield losses of approximately 65% once we have those abnormal ears. So moving on with some of our research highlights, up to this point, these ear issues are still affecting cornfields, not only in Nebraska, but also in the region. They reduce productivity, and we as researchers, we continue with the major task to investigate the responsible factors or causes. The results have indicated that weather, genetics, and management, all of them play a role in these abnormal events. It's also clear that after several decades, close to a century of research in corn, the crop is not understood completely. These abnormalities are not still showing the definite causes, and we continue to work on that. Understanding these causes will help us sharing recommendations, hopefully reducing those issues, and at the same time, we will be able to produce more with less, improving our corn systems and cropping systems in general, while we are also being efficient with the use of resources. So just highlighting here our overall approach in this project. It started in 2016 with field service in grower fields in Nebraska. In 2018, we started working with experimental research via university and industry partnerships. In 2020, we established experiments looking at controlled environments. And on 2021, our major focus is to continue working in summarizing results and getting these results communicated, delivering our outcomes. And with that, thank you, and hopefully we will have some time for questions.
Thank you, Osler. We will go into the question and answer period, so please type your questions in the box. We will kick off this this section with a question. We'll start off with a question for Jeffrey Westrop. And the question is, what can we do, or how can we reduce uranium mobilization in groundwater? And what is the role of agriculturalists in the process?
Okay. So I'm just going based off of my research, which is that we found links between nitrate and uranium, and these have also been in, agricultural plots of land. So if I were to think of role just specifically of like an agriculturalist, it would be good to find ways to, increase the uptake of nitrogen fertilizers, just by the plants, so that you don't get a lot of that, microbial nitrification and then leaching of nitrate into the deeper parts of the aquifer where uranium mobilization can occur.
Very good. A question for Osler. And I'm going to do a little bit of creative modification of the question and add to it. And it's about, have any of your experiments revealed relationships between fertilizer application, timing, and the ear deformation? And I was going to add on of the different environmental, the different stresses that you looked into, environment, of genetics, right? What is your feeling is where the most likely reasons for these deformities to occur?
Thank you very much for the questions, Jackson and Dr. Neal. So answering the first half about fertilizers and timing, when we look at these affected fields from the growers' perspectives, those were fields that were high intensification, high fertility programs, good pest and disease management programs. So they were certainly fields shooting for high yields. And so we have replicated that over our experimental research, meaning that we go strong with our fertility, making sure that that's not a limitation. And still, with those conditions, we are able to document these abnormalities happening. So that takes the fertility slightly out of the question at this point. Now, on the second half of the equation, which is what are some of the ideas that we have, where are the stresses or the causes coming from? So certainly genetics, we have been able to document that specific hybrids are most susceptible to these issues as compared to other lines. Definitely the environment plays a role. There have been events where we documented cold start of the season in the spring, sometime April or May. We have also research questions going around solar radiation that we need to look into deeper relationships. And on the greenhouse side, we have been studying temperature stress, and we have been able to see some responses along that, as well as growth regulators. So those are some of the things that we have been able to see. We are in the process of putting all this together, writing different chapters with different results, and hopefully getting that out sometime this year.
Thank you. Well, adding to getting that out question, once you have the results and they're in publishable form and so forth, how do you get that information to the farmers, right? So that they can learn from it.
Well, very good point. Yes, communication, the second speaker was talking about that, is as important as doing the science, as doing the research. So actually, over the years, since our project started here at UNL, we have been active participators in the extension programs, not only here in Nebraska. In fact, I have been able to present some of our results international audiences via invited presentations. So we are already doing some of that, and I wish we will continue doing so by translating scientific peer-reviewed publications into CropWatch articles, for example, which are most read by our practitioners, not only in Nebraska, but also in the region. So those are possible means to communicate to the different groups what we are able to learn.
Okay, thank you, Osler. Jas, a question for you. So you've been using unmanned aerial systems in your research. Where do you see that type of, where do you see the future of the use of these systems in agriculture?
That's a great question, Christopher. I genuinely feel that the use of unmanned aerial systems in agriculture would increase exponentially in the coming years. And the reason for that is it actually brings out a lot of labor and tediousness of the real-time monitoring of from the sensor node station. So yeah, we can have our sensors and everything installed within the field, but yeah, having the drones or the UAS collect the information from the field would eliminate the effort that would be required to manually going to the field and collecting everything. So I guess they are already being used in a lot of agricultural applications, including the wireless sensor networks. And I feel that, yeah, it's going to increase in the coming years.
And how about the Internet of Things angle?
Yes, that's a very interesting aspect, actually. So the Internet of Things would actually help you, take the decisions, by itself. So we can actually input, a few parameters into the system that would actually help the system take the decisions by itself. So, when the UAS would communicate with a few sensors, and then the whole system would be informed that, yeah, that's the current status, or when we're doing the real-time monitoring of the field parameters, that's where we are. And then based on that, the system by itself will, make the decisions for how much water to apply and when to apply, and various fertigation actions would be taken by the system by itself. So yeah, I think Internet of Things in agriculture has got a great scope.
Thank you, Jas. And before we move on, I'm going to do a quick round of last questions, starting with Jeffrey, as he's finishing his PhD. What are your next steps in your career? And Jas and Osler, be ready to respond the same thing, okay?
Definitely.
Jeffrey?
Well, right now I've actually been thinking more of getting into like more, I want to say government or public work, because like I've worked with several landowners and stakeholders, and I just enjoy that type of work, like being able to actually address their groundwater concerns. The research is a lot of fun, but I'm looking more into jobs like the USGS or School of Natural Resources, or areas where I could work with stakeholders.
Thank you, Jeffrey. Osler, what are your future career goals?
So I have started actually in the process of looking into faculty positions here in the US, ideally Midwest locations, since I have been working with research here in the last, probably 6 years. So working into that, and we will see what future brings.
Okay, thank you. Jas, do you want to wrap this up?
Yes, definitely. As of now, since in the last spring season, I just developed the data mule system. So this summer, I'm looking forward for additional testing and validation. And after that, I would be, equally inclined towards both industry and academia. I'll be looking for the faculty positions around over here in Midwest, and at the same time, I'll keep the job hunt for industrial positions as well.
Thank you. Thank you, the three of you, for your presentations and staying on time. Virtual claps to you. We'll move to the second rapid round of presentations. We're going to start the second round with Chuyang Liu. He's a PhD candidate studying water resources engineering. He's under the advice. His advisor is Yu-Song Lee, Associate Professor in Civil and Environmental Engineering. Chuyang is going to talk about uncertainties in atrazine leaching and accumulation. Chuyang, the floor is yours.
Thanks. Hello, everyone. I'm Chuyang Liu, a fourth-year Ph.D. student from Department of Civil and Environmental Engineering at the University of Nebraska-Lincoln. My advisors are Dr. Yu-Song Lee and Dr. Shano Patel-Hunt. The topic of my presentation today is uncertainties of atrazine leaching and accumulation under future climate scenarios on the irrigated corn production areas. A little bit of background information. Atrazine, one of the most widely used herbicides to control weeds, is commonly detected in groundwater and surface water. However, atrazine is also an endocrine disruptor, so EPA set a maximum contaminant level as 3 microgram per liter. With increasing demand on global agriculture production and the need to maintain sustainable water resources, it's important to predict the leaching and accumulation of atrazine in the weather zone beneath agriculture production areas. The study site we choose called Nebraska Management System Evaluation Area in central Nebraska. It has a shallow groundwater table, sandy aquifer weather zone. Average atrazine concentration is around 1.57 microgram per liter. It also has really heavy annual use of atrazine. The research objective for this study is to analyze inferences of uncertainties on predicting the leaching and accumulation of atrazine in a center period irrigation corn production site. In this study, we analyzed 20 future climate scenarios from year 2056 to 2059. Excuse me. Those climate projections are under representative concentration pathway 8.5, which has high greenhouse gas emission pathway. The figure on the left are total annual precipitation in future years alongside historical observations. The figure on the right side are percentage change in total annual precipitation relative to the historical mean. In this plot, we can see that the large climate variability exists. The percentage change could be varied from around negative 60% to around 75%. We has a relatively small, around 9% rise of average total annual precipitation. Excuse me. So similarly, we can plot the total annual UV transpiration in future years alongside historical observations and the percentage change. From this percentage change, we can see that we have around 12% increase of annual total UV transpiration. The increase of total annual UV transpiration can offset impacts of increased total annual precipitation on groundwater charge. And consequentially, groundwater elevation through the flow model will accumulate the variance and gradually decreases from the 612 meters to 610 meters. Declining groundwater in future may aggravate the problem of overdraft of local aquifer. Irrigation in the northern high plains aquifer for agricultural productions mainly comes from the groundwater. Unsustainable groundwater storage in future may constrain or reduce agricultural production, similarly to the situation in the high plains aquifer of Kansas. In this study, we also look at the atrazine mass accumulation. Here I show a map about the maximum annual mass over the years and also minimum annual mass over the years. Similarly, we also have the percentage change relative to the historical mean. From the plot B and plot D, we can see the large variation exists for the annual mass, which is clear to show that different climate scenarios have great impacts on atrazine and mass accumulation and migration. For a quick summary, declined groundwater elevation in future may aggravate the problem of overdraft of local aquifer. Secondly, different climate scenarios have great impacts on atrazine and mass accumulation and migration. Thanks for the funding support and thanks for listening.
Thank you, Chuyang. We will get back to you with questions after the next presentation. The next and final presentation of this morning is by Jackson Stansell. He's a master's student in agriculture and biological systems engineering. His advisor is Dr. Joe Luck, who's an associate professor in the same department, and he's working on fertigation and data-driven decisions for fertigation management. So Jackson, you have the floor.
Awesome. Thank you, Dr. Neal. So my presentation today is Fertigation Forward, Data-Driven Decisions for Fertigation Management. I'm Jackson Stansell, master's student in agricultural and biological systems engineering. Dr. Neal mentioned Dr. Luck is my advisor. I'm also working with Dr. Darren Rudnick, Brian Cranky, and Hongfang Yu from over in the computer science and engineering department. So to get started with some motivation for why we're looking at fertigation and why we're trying to drive fertigation forward is that, number one, groundwater irrigated acres are vulnerable to nitrate contamination. We know this well in Nebraska. Many of the wells here in Nebraska are over 10 parts per million, which is the maximum contaminant load mandated by the EPA for safe drinking water. But this is not just a Nebraska problem. Kansas, Oklahoma, Texas, Southern Georgia, Maryland, a lot of other places in the US also have these issues with groundwater nitrate contamination. On these groundwater irrigated acres, fertigation is used on approximately 25% of sprinkler irrigated corn acres. So that's not all groundwater, but fertigation is a really common practice within sprinkler irrigated, center pivot irrigated corn acres within the United States. And that 25% holds true for Nebraska as well as the rest of the United States. Optimizing our nitrogen use efficiency within these irrigated production systems is really important and has two key benefits. Number one, we reduce our overall environmental impacts, and this extends to groundwater as well as to greenhouse gas emissions and various other aspects of environmental quality. And the second benefit is increased profits for farmers. If you can reduce the total amount of nitrogen needed to grow the same or better corn yields, then overall you're going to increase your profits on your farm. So what we've been working on, a lot of these fertigation systems right now are managed qualitatively using grower experience, some sort of non-quantitative recommendation or something like that. And so what we have started to develop as a research group is what we call sensor-based fertigation management. And so we've developed a framework that basically generates binary decisions on a week-by-week basis for fertigation management throughout the growing season. So that framework begins each week with imagery collection, either from drone or satellite platforms, and we get multispectral imagery out. We process that imagery to turn it into a single cohesive image of the entire field. With drone imagery, this requires stitching. With satellite imagery, there's usually no additional stitching processing involved. And once we have that cohesive image, we're able to actually pass it through an analytics algorithm that we've developed that characterizes each area of the field that's under sensor-based fertigation management for its level of nitrogen sufficiency. And so this basically says, okay, what is the nitrogen status of the corn? Is it good to go for another week, or does it need fertigation in this particular week? And so based on that analytics layer that is generated, we're able to make fertigation decisions for each managed area within the field and ultimately generate a fertigation prescription that can be submitted to a pump and center pivot irrigation system within the field to execute that application and do it in a way that really reduces the overall amount of manual input that is required from the farmer who is going to implement this process. So we've tested this framework, various versions of the framework using different parameters and combinations and some on-farm research trials, 10 total on-farm research trials between 2019 and 2020. And these were on commercial scale corn farms that are located in primarily areas of the state that have really high groundwater nitrate concentration levels. We're trying to bring this research to the areas that are most impacted and most likely to be impacted by regulations for nitrogen in the near future. We had a total of 6 cooperating farmers, and we looked at 3 treatments per site, 2 sensor-based fertigation treatments, and 1 typical grower management treatment. Between the 2 years, we looked at 3 different sensor-based fertigation management approaches. So looking at kind of our site level results, if we think about taking the difference between our sensor-based fertigation management treatments and typical grower management in 2 major metrics, one being marginal net return, which is essentially profitability, and the other being partial factor of productivity, which is a measure of our nitrogen use efficiency. What we found is that all sensor-based fertigation management treatments resulted in median increases in partial factor of productivity, which is our nitrogen use efficiency, up to 15 pounds of grain per pound of nitrogen. And so with that, we're essentially increasing by 33% the efficiency that these growers can produce the same amount of corn with obviously less nitrogen. We also found that all sensor-based fertigation management treatments resulted in median increases in profitability, some of them up to $8.23 an acre, which is a fairly substantial amount of money for a farmer if you consider that a typical quarter section here in Nebraska is 160 acres, of which about 130 are irrigated. So these are pretty substantial results. And I think even to provide a little bit more context, in all of our implementations of sensor-based fertigation management in these on-farm research trials, we found that 94% of the implementations resulted in higher efficiency than typical grower management. So this means that we were using less nitrogen to produce essentially the same or better yields on these farms. And that is a statistically significant finding. There was no difference in yield or profit that was attributable to SBFM. So even though we had those median increases in marginal net return, there really wasn't a statistically distinguishable difference in profit when averaged across all the sites. And we did find that we had a reduction of up to 45 pounds of nitrogen per acre in average total nitrogen applied with sensor-based fertigation management versus the management that growers are putting out there on their fields today. So since this is kind of a practice that we'd like to see adopted commercially, we want to think about scaling sensor-based fertigation management. There are 3 key barriers to scaling and adopting sensor-based fertigation management. One is time demand, the next is error potential due to the computational complexity, and the third is cost. And so in order to kind of get past these barriers to adoption, we really realized that sensor-based fertigation management execution has to be automated with software. And so kind of the last stage of this project for my master's so far has been developing the in-time fertigation management system, which is a unified specialized software platform that is dedicated to sensor-based fertigation management. And so it's able to automate these weekly processes and basically reduce what could be a 2-hour time commitment down to 7 minutes or less per field. And so in conclusion, sensor-based fertigation management has proven to be a more nitrogen use efficient approach to fertigation management than typical grower management. And this isn't just typical grower management. These are guys who are already, guys and girls who are already implementing best management practices on their farms and really splitting out their applications. Profit outcomes are less consistent, but we need more trials and more data to be able to really hone in on what those impacts are. And finally, sensor-based fertigation management can be automated to enable use at scale. And with that, I'd like to say thank you, and thank you to Water for Food for supporting this research, as well as the Nebraska Corn Board and Central Platte Natural Resources District.
Thank you, Jackson and Chuyang for your presentations. Let's do some question and answer here. So remember, those who have questions to put it in the chat, in the question and answer box. Let's kick off with a question for Jackson. And you've partially touched on this subject, right? First, is it financially feasible for farmers to implement some of these technologies, right? Does the profitability that you showed make up for the cost of implementing some of these systems or paying for a consultant or whatever it is involved in reducing nitrogen application or applying it spatially and so forth? Could you comment on that, please?
Sure. So this is something that I've been asking a lot of questions of growers in a lot of different places here recently about. And to kind of answer it indirectly, a lot of farmers are starting to use granular, which is a model-based method for determining their nitrogen programs. And granular is currently charging $6+ an acre for those agronomy services. And so I guess what I know is that farmers are willing to pay $6 or more an acre in order to cut back on nitrogen. And so with looking at ROIs of somewhere around $8, $6, maybe $10, somewhere in that range, I do think that it is significant enough for farmers to think about adopting. But it's really hard to tell until that product gets out there and a farmer uses it for 3 years, you know, whether or not their decision is going to be to stick with it. So I think ultimately we're going to have to look at some other aspects of what the real return is, kind of even a social cost of nitrogen, so to speak, that's, you know, kind of enforced by taxes or something along those lines, to think about what the real cost benefit would be.
Thank you. A question for Chuyang. So since atrazine accumulation and migration in corn production areas are greatly impacted by climate, what is the solution beyond addressing climate change, or are there other multiple factors that can be adjusted to cope with the changing climate?
Excuse me. Thanks for asking that good questions. And sorry, I do not have enough time to show another results. From my previous presentation, I showed that climate variability has a huge impact on atrazine accumulation. But in the further study, we also found that changing soil properties, like the atrazine degradation coefficient and absorption coefficient, could hugely mitigate this problem. So I believe this message could be helping farmers adapt to the climate change with sustainable water resources.
So let's see if there are any other questions. There's one for Jackson. How do you think the current market scenarios for the price of corn and nitrogen are affecting your profit results?
So profit results wise, I haven't rerun our profit calculations with the current numbers for this year. I would imagine that they would make sensor-based fertigation management significantly more profitable. But nitrogen tends to follow corn prices, and so it may not be quite as big an impact as you would expect. I think the bigger impact is really more on whether or not growers are willing to test out some of these technologies. Because I've had several farmers who have indicated that they are more likely to invest in this type of technology under the current market scenarios. And I've also had a farmer that we've worked with now for 3 years on this kind of research. He's wanting to put this on as many fields as he can because of how high nitrogen costs are getting. And so that nitrogen cost really does drive how much guys are wanting to look at putting this on their farms.
Thank you. And as we complete, I'm going to ask you for the same question that I ask the other students. What next after you finish your degree? Chuyang, do you want to start off, and then Jackson can answer the same question?
Oh, sure. I would like to find a postdoc position first, then find a faculty position. Yeah. Thanks.
Okay. Jackson, what are your goals?
Sure. So after defending my thesis on this coming Thursday and finishing up writing it in April, I'm planning to start a Ph.D. here at the University of Nebraska in May, kind of working on developing an IoT and an automated solution for high resolution fertigation. Beyond that, we're also kind of looking into commercializing the sensor-based fertigation management approach to be able to get it in the hands of people to actually use and benefit from. So it's not just grant supported and potentially short term.
Great, thank you. So we have come to almost the end of our program, and I wanted to just point out, thank you all the speakers for their presentations. And I wanted to point out that if you look at, there's a common thread in all these research presentations, right? We have a common thread of climate, nitrogen management and greenhouse gas emissions. And I think really that the future for that agriculture is part of the solution in the future if we can help the farmers monetize their carbon storage, right? And also decrease the greenhouse gas emissions from nitrous oxide from fertilizer and other farm activities. I think that's going to drive this market in the future and help agriculture become part of the solution. So anyway, thank you very much, everyone, for your talks. I will pass the word on to Rachel for some final comments.
Thank you, Christopher. Again, I'm Rachel Herpel. I'm the Assistant Director of Daugherty Water for Food Institute, and I'd like to thank everyone for being here. We enjoyed seeing the students present. Also hearing from astronaut Clay Anderson and Dr. Martha Shulski. Again, I want to thank everyone for being here, but also to thank Christopher for moderating. You always do an excellent job of bringing all the students together and highlighting their work. Also want to thank Francis Hayes and Amber Poitras for organizing this year's event and doing all the support of the students to making sure that they're here and sharing their research. I think Francis just shared the link to the student research impact statements. So we encourage you to visit those, and there are a lot of other students that are that we weren't able to share their research in this amount of time, but do take a look at those. Thank you again, and have a great day.